As we saw with Dalton's atomic theory, if we want to quantify a chemical process, we need to keep track of how many atoms, or at least how many moles of atoms, are present. But we don't have a machine that directly measures the number of moles. The most common quantitative measurement on a solid, like this zinc metal, is to put it on a balance and measure the mass. But how do we know how many moles are there or how many atoms? This is a process called stoichiometry. The word stoichiometry comes from the Greek word stoichion, which means element, and metry, which refers to measuring. When we want to quantify a material or a reaction, we talk about its stoichiometry. Often we will have one quantitative piece of information about a material or reaction and want to know something else. For example, we may measure the mass of a material on a balance, but want to know how many atoms or molecules are present in that sample. There are a number of mathematical methods for handling numbers. We will use the conversion factor approach. If you have taken chemistry before, you have been introduced to at least one of what are many different strategies for solving stoichiometry problems. For quantifying elements, we'll describe a one-step method that's based on what is in a mole. In the one-step method, we will have to employ 3 skills: reading, chemistry, and math. Many of the questions will describe situations where we know one quantitative piece of information about a sample, and we want to know a different piece of information. We will need to read the problem to see what units we are converting between. The only chemistry we need to know is what is in 1 mole of our substance. Remember that the mole is the standard or reference amount of a substance. Finally, we will use our math skills to construct a conversion factor to solve the problem. Let's use this approach to solve some problems. Our first example asks, what is the mass of a 2.65 mole sample of copper? First, we read the problem to see that we are asked to convert from moles to mass, which will be in grams. Next, we use our chemistry skills asking what is in 1 mole of copper. Well, there is 1 mole in 1 mole, and the periodic table tells us there is 63.55 grams in 1 mole. While it may seem silly at this point to ask how many moles are in a mole, this approach will be quite useful to us when we quantify compounds. For example, in water, there are 2 moles of hydrogen in 1 mole of water. This method allows us to perform all of these problems in one step. Finally, we do the math. Start with the quantity given and construct a conversion factor with moles on the bottom and grams on the top. We put moles on the bottom so that moles will cancel out. The mass is 168 grams. Our next example asks how many moles of aluminum do 4.90 times 10 to the 22nd aluminum atoms represent? First, we read the problem to see that we are asked to convert from atoms to moles. Next, we do the chemistry, asking what is in 1 mole of aluminum. There are Avogadro's number of atoms and 1 mole in 1 mole. Finally, we do the math. Start with the quantity given and construct a conversion factor with atoms on the bottom and moles on top. The answer is 0.0814 moles. Our last example asks how many atoms are in a 5.65 gram sample of beryllium. Again, the first step is to read the problem to see that we are asked to convert from grams to atoms. Next, we do the chemistry, asking what is in a mole of beryllium. The periodic table tells us there are 9.102 grams. We also know there are Avogadro's number of atoms in 1 mole. Finally, we do the math. As usual, start with the quantity given and apply a conversion factor with grams on the bottom and atoms on top. The answer is 3.77 times 10 to the 23rd atoms. You may have learned to do a problem like this in a stepwise fashion. In the stepwise method, you would use the fundamental conversion factors of molar mass and Avogadro's number. Since we are given grams of beryllium, you would first convert grams to moles using the molar mass. Note that the units of molar mass are grams per mole. Then moles would be converted to individual atoms using Avogadro's number, whose units are atoms per mole. In this case, both conversion factors would need to be used in consecutive steps. First, molar mass is used, but used upside down, canceling out grams. Then Avogadro's number is used right side up, canceling out moles. The result, of course, would be the same. In each case, we are multiplying by Avogadro's number and dividing by the molar mass, so the numbers you enter into a calculator would be the same. There are a number of ways to set up these calculations. We showed the one-step method. There is also the stepwise method. Rather than writing explicit conversion factors, you may have learned to put numbers in boxes like this. Note that not every box has a number in it, which can be confusing. You may have learned to solve these problems using ratios. Please note that there is no one correct way to solve these problems. If you find one method easier, you should use it. When it comes to quantifying compounds later on, you may find that the one-step method is easier for you. Pick whichever way is most comfortable for you. Whatever way you choose, you need to practice that method so it becomes automatic for you. If you've never done this before, or if you used a different method but are not really sure about it, I would recommend the one-step method. But ultimately, you need to use whatever method works best for you.